plant density, an overview. Density is a commonly measured attribute that we use to quantify and describe vegetation. Density is defined as the number of individuals per unit area. Now, sometimes with certain species, it can be difficult to determine what is an individual. And when we run into this difficulty, and if it's not necessary to know whether we're dealing with individuals, density can be defined as the number of counting units per unit area, and then we need to clearly identify what a counting unit encompasses. We use density measurements to describe the closeness of individuals to one another. And so it relates to the way that individuals occupy space in a landscape or an environment. Now, density and abundance are two terms that are often used synonymously, but they are in fact quite different. And so we're going to take a look at an example in which we compare populations of two different states in order to examine the difference in these two terms. And here we're going to be focusing on the populations of Arizona and Tennessee based on the U.S. Census Bureau census that was taken in 2010. The populations of these two states is actually quite similar, coming in at just below 6,400,000 for both of them. Arizona, the size of Arizona's population is just under 1% larger than the population of Tennessee. Now, they do differ significantly in their land area. Arizona is slightly over 113,000 square miles, whereas Tennessee has a land area that is 41,217 square miles. So the size of Arizona is approximately 2.76 times larger than that of Tennessee. Now, this is where we can see the difference between these two terms. If we talk about the abundance of the two states, we're simply talking about the number of people per state. And we've already noted that they are nearly equal. But density, as you will recall, is reported in units of the number of individuals or the number of counting units per unit area. So in this case, the individuals are individual people, and the unit area is per square mile. The density of Arizona is 56.3 individuals or people per square mile, and the density of Tennessee is 153.9 people per square mile. So Tennessee's density, the density of their population, is 2.7 times greater than that of Arizona. There are a number of uses for density data, and most commonly we use density data when counts are appropriate. In natural resource studies, this usually relates to demographic studies, such as studies of population dynamics, where we're looking at age structure, and we are interested in rates of recruitment and mortality. We also use density data when we're interested in getting information for revegetation or reseeding projects. For example, if we want to quantify the amount of recruitment of seedlings that we've had after a certain action. Density data are also applied for conservation purposes, particularly if we're interested in monitoring populations of rare species or invasive species. Oftentimes we're interested in when these populations are nearing threshold values, whether they are becoming decreased in size or increasing in size, or if they're responding to management. And finally, density is used as an indicator, both as an indicator of population stability as well as to indicate trends or rates of change. And so these have direct applications to inventory and monitoring purposes. Now, one of the primary weaknesses of density data is that density does not relate to dominance or importance. And so it doesn't do a good job of reflecting resource use. If we look at this schematic of a plot in an area, we can see that there are 2 green individuals represented here, and there's also 20 of the smaller red individuals. The density of the red individuals, or the red types of plants, is 10 times greater than the density of the green species. But it's fairly obvious that in this case, the green species are more dominant. Biomass and cover are attributes that are much better indicators of ecological importance and ecological dominance. Now, whenever we're going to be measuring density, we always need to consider ground rules. That's true for all of the attributes that we measure. And primarily, our management objectives drive our ground rule decisions. One of the important ground rule decisions that we need to make when we're concerned with density is to clearly define the counting unit. This can include an individual if we were, for example, interested in a population level type study, or we may be interested in different plant parts, such as the number of stems, or the number of inflorescences, or even the number of flowers. It all depends on what the reason why we are collecting the data. Another ground rule that is important is the level of identification that needs to be done. Oftentimes in ecological studies, we're interested in collecting data at a species level. But depending on how we're going to use that data and what the purpose is for collecting the data, we may not need to identify to the species level. It may be sufficient for us to identify to the genus level. So instead of Bouteloua areophyta or black grama, it would be sufficient to say that we have a grama grass or Bouteloua. Likewise, sometimes we're just interested in the functional group. We just want to know if it's a perennial grass or an annual grass or a forb or a shrub. There are other ground rules that are applied, and they are specific to the different methods that are used to measure density. Now, there are 3 main approaches to measuring density. This is the use of abundance classes. There are also a group of counting methods and distance methods. With abundance classes, this is a visual rating system, and it is a very rapid approach. It's good for large-scale surveys because it can be done relatively quickly. And with this approach, we make estimates that use a range of scarcity to plenty. So here are a couple of common classification systems that are used when we're talking about abundance. We could say that plants are either very rare, rare, occasional, abundant, or very abundant, or another approach is to describe whether they are very sparse, sparse, not numerous, numerous, or very numerous. Now, one of the abundance class method provides qualitative data, and one of the disadvantages or difficulties with using this approach is that it can be very difficult to ensure consistency. Of course, you would train your observers so that they are properly calibrated, but it can be difficult to get the same kind of results or consistent estimates if you are using different observers in the same location, or even for one observer to be consistent if they are comparing different vegetation types at different locations. Counting methods are another major approach to estimating density. These are plot-based methods, meaning that they use quadrats or frames or plots. Now, quadrats can come and plots can come in various sizes and shapes based on the needs of the studies. Here we see a picture of quadrats that they are square, some are rectangular, and some are circular. Generally, when we're using quadrats, these are frames that have hard edges, and they need to be carried to the plot, so they have to be relatively small. Sometimes we may want to measure in larger plots, and in this case we can stake out the corners of the plots and use transect tapes in order to determine the different dimensions of these plots. In other cases, we may want to use plots that are even longer and narrower, and we have a special term for these, which is belt transects. With counting methods, the size and the shape that we choose for the quadrats depends on plant size and dispersion. So if we start with small quadrats, we could go to larger quadrats or to larger ones still. In general, as the size of the quadrat increases, we tend to include more of the larger individuals and also tends to cut across clumps. The shape of the quadrat also makes a difference. What our choice of shape is also driven by the size and the dispersion of the plants of interest. And we generally find that as we go from square to rectangular and to even more narrow and more rectangular, that we can cut across clumps. And in general, we would make these types of decisions, or this would be a good choice in scattered vegetation or where the vegetation is sparse. And finally, sometimes we are interested in estimating the density of diverse life forms, so multiple species that have different sizes of individuals, or they may have different dispersion patterns. And in this case, we use nested quadrats. With nested quadrats, you have a smaller quadrat that is embedded inside larger quadrats. And this is used when we want to estimate density. We measure density in these different quadrats simultaneously. One of the disadvantages of quadrat or plot-based methods or counting methods is that there's the potential to have errors occur at the boundaries, and this is called edge effects. And that brings us to the last main method of estimating density, which are called distance methods. Distance methods are plotless, and so because of this, it eliminates edge effects and the potential for error caused by having to make decisions on the boundaries of the quadrats and plots. With distance methods, we measure the distance between plants. And this is most often applied in forested or woodland situations or in some shrublands. Usually when the focus is on only one or two species, and they can be spaced either closely or spaced at distance. The unifying concept of distance methods is the mean area concept. Mean area is inversely related to density. The units of mean area is the average area that is occupied per plant. And it's very easy to see that this is the inverse of density, whose units are the number of plants per unit area. The most commonly used distance methods are nearest individual, nearest neighbor, random pairs, point-centered quarter method, and the wandering quarter method. More information about the application and use of counting methods and distance methods will be provided in subsequent lessons.